everyone, I'm Danny. Now I would like to talk about the experiment T1, which is the equations of state of ideal gases, and discuss its SCP-2821 Physics Practical 4. Let me introduce my turns. My name is Danny Ling Walai, and my partners are Ling Len and Ling Xiaojun. Our lecturer is Dr. Muhammad Arif bin Jaring. Let us from the objective of these experiments. Firstly, to measure the volumes of a current of air as a function of its temperatures at constant pressures, Charles' law. Secondly, to mention the volumes of a current of air as a function of its pressures at constant temperatures, Boyle's law. Thirdly, to mention the pressures of a current of air as a function of its temperature at constant volume, Amonton's law. Lastly, to determine the expansion coefficients of a pressure coefficients beta and the compressibility kappa of air. There are some apparatus that are used in these experiments, which are gas law apparatus, emissions thermostat, temperature vane, and thermometer. Let's talk about some theories of these experiments. The state of a gas is given by the state variable temperature, pressures, volumes, and the amount of substance, which iteratively determine one another. Thus, the dependence of the volumes on a variable temperatures and pressures at a constant amount of substance is given by the following total differentials. The equation 5.1 is shown. Analogously, the following is valid for the change of pressures with temperatures and volumes. The equation 5.2 is shown. The partial differential quotients theta t theta p times p theta t theta p times b and theta p times t correspond geometrically to the stroke of a selected state functions b equal to ft, b equal to ft, or b equal to fp, and thus characterize the dependence of the variable bp on the respective step variable tp. Their value are dependent on the initial volume b0 or the initial pressure p0. Therefore, one defines the following intensities variables by reference then to b0 or p0. That is, the p or p at t0 equal to 273.15 kelvins. The equations 5.3, 5.4, and 5.5 for the limiting case of ideal gas. Thus, relationship can be derived from empirically determining law, which each describe the correlations between two step variables. For isobaric process control, p equal to constant, dp equal to 0. Equation 5.1 become equations 5.6. For alpha equal to constant, the integrations of these differential equations results are shown as the equations 5.7 and 5.8 or 5.9 or 5.10. In accordance with these correlations, which was discovered by gas losers, the graphics presentations of the volumes as a functions of the temperature supplies icing strength line with p equal to 0 for t equal to 0 and isochoric conditions p equal to constant, dp equal to 0. The following results analogously from equation 5.2 is shown as equation 5.11, and from the integrations with beta equal to constant, the integrations of these differential equations are equations 5.1 and 5.12 and 5.13 or 5.14 or 5.15. Those equations are expressions of Charles Amonton's law and describe the linear increase in the pressures with increasing temperatures. For the isothermal expansions and compressions, T equal to 0, dP equal to 0 of a constant quantity of gases, the following is valid as equations 5.16 or 5.17 or 5.18. The graphic presentations of these correlations, which was investigated by Boyce and Mariti, result in hyperbolas for b equal to fp in contrast for b equal to f1 over p. Straight line are alternate. If the volume of the substance is constant, then dB equal to 0. So from equations 5.1, the partial change of pressures with temperatures can be written as equation 5.19. Combining equation 5.4 and equation 5.19, the following equation relate alpha, beta, and kappa is shown as equation 5.13. Next, let us talk about the procedures of these experiments. To begin with the water circulating systems, the thermostat water bed is filled with distilled water up to the level at which the heating coil is fully immersed. The temperature control node is set to an initial temperature value. The main power supplies and the power switch on the thermostat, which are switched on. The water circulating systems is checked to ensure correct operations. The thermometer's reading is recorded only after the water temperatures has stabilized. To note that the gas temperatures is read from the thermometer, not from the thermal temperature control node. The water water circulating system is kept running at all times, and the cooling coil is used to cool the water if necessary. Besides that, we will look at the measurings of B as a function of P at constant T. The top of the mercury reservoir in tube B is removed. Tube B is raised or lowered until the mercury level in tube A and B are equal to the height L of the air columns in tube A, and the temperatures reading T are recorded. Tube B is raised to a new height, and the height difference theta h between the mercury level in tube A and B is recorded from the scale readings. The newest height of the air columns in tube A is recorded. Step 4 and 5 are repeated for at least 6 pairs of delta H and L, and all data are recorded in table 1. Moreover, let us look at the measurings of B as a function of T at constant P. The temperature control knob is set to the initial temperatures. The thermometer reading T is recorded after the temperature has stabilized. The initial height of the air columns in tube A is recorded. Step 1 to 3 are repeated for at least 6 pairs of T and L, and all data are recorded in table 2. To note that the temperatures must not exceed 80 degrees Celsius, and the pressure is kept constant by adjusting the mercury level in tube A and B to the same height. In addition, we look at the measuring of P as a function of T at constant B. The height L of the air columns is set to a suitable value by adjusting the positions of tube A, and this value is recorded. The initial temperature is recorded after the thermometer reading has stabilized. The initial pressure is determined by measuring the height difference theta h between the mercury level in tube A and B, and the value is recorded. The temperatures of the air is increased using the temperature control knob. The volume of the air is maintained at its initial value by adjusting the height of tube. The new temperature T is recorded after stabilization, and the new pressure is determined from the height difference theta h between the mercury level. Step 4 and 5 are repeated for at least 6 pairs of T and delta h, and all data are recorded in table 3. The volume and pressure calculations are used the equation 5.21 and 5.22 to calculate the volume and pressure of the air in the columns from the value of L and delta h. The table 1 is short. The table 2 is short. The table 3 is short. Now I will pass it to my partner, Lin Xiaojun, to discuss about the analysis.
Hi everyone, I'm Lin Xiaojun, and I'm in charge of the data analysis for this experiment. Moving into the analysis, we analyzed the relationship between the state variable of the air column through 3 primary graphs. First, to verify Boyle's law, we reported pressure against the inverse of volume. As expected, we observed a strong linear correlation with our best fit line following the equation y equal to 16.943x minus 7.768. Next, we look at the temperature dependency. For Charles' law, the V versus T graph yield a gradient of 4.11 times 10 to the power of negative 2 ml per degree Celsius. Similarly, for Emeter's law, the P versus T graph show a steady increase with a gradient of 0.29 kPa per degree Celsius. These linear trends confirm that the air in our column behaves closely to an ideal gas within the tester range. Using the gradient and intercept from this regression, we calculated the 3 fundamental coefficients for air. To find the expansion coefficient, we took the ratio of our Vt gradient to the initial volume V0. This resulted in an experimental value of 2.91 plus minus 0.34 times 10 to the power of negative 3 per Kelvin. We apply a similar methodology for the pressure coefficient, utilizing the PT gradient and the initial pressure P0 of 96.52 kPa, giving us 3.0 plus minus 0.35 times 10 to the power of negative 3 per Kelvin. Finally, we determine the compressibility using the relationship between alpha, P0 and beta. Our calculated compressibility is 10.05 plus minus 2.48 times 10 to the power of negative 3 per kilopascal. Regarding accuracy, we obtained a percentage error of approximately 20.5% for alpha and 18.1% for beta. However, our compressibility was only 1.8% error. Now I will pass it over to Limler for the discussion.
I'm Limler, and now let's move on to the discussion. Gases has various properties such as gas pressure, temperature, mass, and volume, and careful and scientific observation has determined that these variables are related to one another, in which the values of these properties determine the state of the gas. Then, the 3 empirical laws established from early experimental studies are Boyle's law, Charles' law, and Gay-Lussac's law, which is often associated with Edmonton's law, and these 3 empirical laws can be combined into a single expression that describes all the relationships simultaneously, which is the ideal gas equation of state PV equals nRT. Thus, these are the objectives of this experiment. So firstly, for task 1, the graph graphs of pressure versus inverse volume, volume versus temperature, and pressure versus temperature were plotted using Excel, and the plotted three graphs all show a linear shape with positive slope, which are consistent with the three empirical laws mentioned. For task 2, the slopes, y-intercepts, and their respective uncertainties of the three graphs were calculated using the least square method, and the obtained linear equation of the three graphs are listed here. As for task 3, the expansion coefficient, pressure coefficient, and compressibility of air were determined using equations from the manual, and the determined values are listed here, and were then later compared to their respective theoretical values. According to the calculated percentage errors, we can conclude that the results are not quite accurate, as the expansion coefficient and the pressure coefficient both have a high percentage error. Then, here we mention about the source of errors, methods to alleviate them, and the precautions of this experiment. So in conclusion, the volume V of a column of air as a function of its temperature at constant pressure, which is about Charles' law, the volume of a column of air as a function of its pressure at constant temperature, which is Boyle's law, and the pressure of a column of air as a function of its temperature at constant volume, which is about Edmonton's law, was successfully measured to the three plotted graphs, which all show linear relationships. Here are the listed calculated values again. Here are the list of references, and that is all from us. Thank you for watching.